So we looked at the components, parts, and operation of hydraulic pumps, and we looked at whether we looked at an engine-driven pump. Here's an example of an electrically driven pump. And so you can see electric motor. Now this is a standby pump, so it's a little bit smaller. This was the 727 standby pump. But again, you have 3 lines going to it. And out of memory, I can't remember which one's which here. These are, I believe, the pressure and suction lines on this end. This, I believe, is the case drain on the top. But here we have an electric motor driving it, and this is very similar to the pump that's being passed around right now. But again, what you don't see here is a depressurization solenoid. So where the engine-driven pumps have a depressurization solenoid on the side of them to be able to shut off flow even if the engine's running. With an electrically driven pump, all you got to do is shut the motor off and it stops the flow of fluid. So they don't need to have the complexity of that extra component or that kind of thing. So a couple others. Here's some other ones kind of tucked down in areas, but electric motor. Here is, the big line going here is your supply, and then you have a pressure lines, usually the medium line, and case drains typically the smallest line. You can see how the head plate on the right labeled D is at a bit of an angle. That's to allow that swash plate or that piston block to move side to side or move at an angle in order to adjust the flow rate. And then another one over here, kind of on the right, similar type of setup, just showing it from a different angle. So hydraulic pumps can also be driven. So essentially you take the same pump that's on an electric motor pump, and you can drive them a couple different other ways. So when you've been doing your labs where you operate the hydraulics on the 720 or 747 in the simulator, you'll remember 2 of those are air driven versus, and then 2 of them are electric pumps for the standby pumps. The 4 main pumps on that where it's got 4 systems are engine driven, and then on those 4 systems, they each have an engine-driven pump, and then they each have a standby pump, and 2 of those are electric, 2 of them are air-driven. So here's an example of an air-driven. I know it's not a great picture, it's an older picture, but you have a pneumatic source that's driving an air turbine over here on the right. Exhaust is the duct going off to the right. And then that's driving a pump here on the left, and say it works the same as any other. You have a supply, a line, a pressure line, a case drain line. It is a constant pressure, variable displacement pump. So just like what you've got there where it can adjust the flow rate. This one does have the integral attenuator, like the pump I brought into class here has, in order to even out those pulses that you get from it being a piston type pump. Okay. Another way that you can power a hydraulic pump is with a ram air turbine. So for an emergency purpose, if you were to lose engines, electrical power on the aircraft, most transport aircraft, you cannot fly without some kind of hydraulic pressure. There is no physical, especially a newest stuff that's all fly-by-wire, or even stuff that was fly-by-cable but made in the last 20 years or larger. There is no physical interconnection between the yoke, the rudder pedals, and the flight controls. Essentially, when you have even those cable-driven ones, the cables are operating hydraulic valves. Okay, the 727 on the ailerons does have a small amount of aileron cable reversion. The yoke can move the ailerons just slightly through the cables, but the rudder and the elevator have to run off of a backup pump. There is no physical connection there. If you go out right now with hydraulics off and you pull back on the yoke, nothing's going to happen with the elevators. Same thing if you move the rudder pedals. If you move the ailerons, you'll see one of the, I think it's the outboard ailerons, will move just a tiny bit. They won't go full travel. Okay. And in flight, that'll be even harder because once you have air flowing across them, it's a lot more force pushing against you. So this is used as an emergency system. Just like the air-driven generators we talked about with electrical, if there's a full, major failure on the aircraft, It's on an arm, a hinged arm. It swings out, a door opens, it swings out from the side or bottom of the aircraft. And then air flowing past, the slipstream flowing past, will turn this turbine blade, which will spin the pump mounted to the back of it. Okay. And the RPMs, just like an air-driven generator, the RPM of it, the pump's looking for, you need a certain number of RPMs to deliver the pressure that it needs to do. That's going to be regulated, in the dome right here. It's going to have a little governor, little mechanical governor, flyweights, right? That will adjust the pitch of the turbine blades. Oops. In order, there we go. I forgot I had a picture. Will adjust the pitch of the turbine blades in order to keep the pump spinning at the speed that it needs to be, even as the airplane speeds up a little bit or slows down, depending on if they're nosing it down more or leveling off a little more. Yeah. It depends, right. So when we did electrical, we talked about something very similar to this, an air-driven generator. It depends on the aircraft. Some have one or the other. I believe there are aircraft, but I can't remember. I think I've seen an aircraft that has both a hydraulic ADG or a hydraulically ram air turbine and an ADG. I can't remember for sure what that was, or if I'm thinking of something else. But I'm fairly certain there are some aircraft that have both. Most of the time when you see them, if they have anything, it's going to be an air-driven generator. And then they may have that can like the aircraft I worked on, the Embraers, the Bombardiers, they have an air-driven generator that creates electricity, and that powers an AC hydraulic pump, AC motor pump. But some of your bigger, this picture is off of, I believe, a 767, where it has a hydraulic pump. And that tends to be a larger aircraft. A 767 is a larger aircraft. I think the 777 has an air-driven hydraulic pump, where they're just too big. And I believe a lot of them do have both. So I'll do some research and get back to you on that. I've got some FAM courses I can look through and see what they say. So we talked about the ports a little bit, but just some close-ups of them. Remember there's a pressure port out to the system. This one's labeled outlet. There's a supply or suction labeled inlet here. And then that case drain with the fluid used for cooling and lubrication. That fluid is going to be filtered, cooled, typically goes through some kind of a heat exchanger before returning to the reservoir. And normally that's the main cooling mechanism for the entire system as well. Often there is not a heat exchanger in any other part of, in the main return. It's typically just in here because the majority of the heat that's going to build up in the system is going to do so inside the hydraulic pump. Remember, in the pump, we're increasing pressure. When we increase pressure, we increase heat. There is a small amount of friction in other places, but really you don't build up heat in your actuators. You don't build up heat where the pressure is being used. You build up heat where you're creating the pressure. And so to cool the most efficient way is to use that case drain to cool the fluid before it returns to the reservoir. Okay. In a similar vein to hydraulic pumps, we have a power transfer unit, or PTU. And essentially what we have here is a pump, a hydraulic pump, a piston pump. If you put pressure into it, works like a motor. So, these aren't like the ones here I'm passing around, they're purely designed as a pump. But the theory behind it is if you back pressure through what essentially is a hydraulic pump, you get what's called a hydraulic motor. So pressure pushing against those pistons can cause it to rotate. So what we have here is, and in some cases it can be a pump or motor, it can go either way. But you have, in this case, a pump and motor that are piggybacked on one another. So pressure, say from the system on the left, can be ported through, causing this to spin, which will then drive the pump motor on the other system. Okay? And this is when we do the 727 to power both the A and the B system, we use the B system on electrical, and then we open an interconnect valve that physically allows fluid to flow between the two systems. They don't do that anymore. Regulations don't allow it, safety concerns don't allow it. Because of contamination concerns, if you have contamination in one system, you don't want it to mix with the other system. Because of a leak, if you have a major leak in one system and it's draining it, you don't want to drain both systems. So a power transfer unit allows us to bring that energy side to side without having any kind of fluid intermixing between the two systems. Okay, so again, the one side would be, say, hooked up to the A system or the number 1 system. The other side might be hooked up to the number 2 system or the B system. And so pressure from one spins, works as a motor. That motor then drives the pump on the other side. And in some of these, they're directional. Power can only be transferred from say, system 2 to system 1, or from system 1 to system 2. Some of them are bidirectional, where either side can act as a pump or a motor. So whichever system has pressure can be used to drive the system that, for some reason, does not have pressure if you have a dual pump failure. Okay, that's actually what's shown if we go way back to the an Embraer hydraulic manual or hydraulic schematic. That's what's shown right here. Here's our power transfer unit. Now this is a single direction one, and what it allows in this case is hydraulic system 1. Well, normally these are some of the most critical, let me think, some of the critical items on the number 2 system, okay? So if you lose number 2, in order to still get landing gear and that kind of thing, when the plane's coming into land, you can kick on this power transfer unit, open this PTU selector valve. That'll send pressure here. You can see which way these little arrows are pointing. It's pointing from left to right, and you've got a check valve. This is a check valve symbol right here to the right of it. So now, in an emergency, if you're down to like the number 1 system, you can operate your, some of your flight controls up here in the top. But if that's, you can also operate the stuff below this PV valve on the right on system 2 using that power transfer unit, where you can kind of fly the plane off of the items that are directly connected to system 1. And then when you get to the ground, when you need to put down landing gear and do nose wheel steering, that you can do that by turning on the power transfer unit to power the number 2 items that are on that kind of emergency section. Okay. There's also emergency parking brake accumulators right here, where you can use either system 1 or system 2 to power the emergency and parking brake. Okay. You can see there are no other backups here, though. This airplane doesn't have a like an air-driven or an air turbine hydraulic pump, but it has enough. It's got 4 AC motor pumps, and it has a air-driven generator that can be used to power certain electrically driven pumps. So that's why it doesn't have one of those air turbine hydraulic pumps. Okay. But skipping back to our PTU, power transfer unit. Here's just another example of one, okay? A little dirtier looking one, because it's in the back of the 727. So in this case, it's directional. You have a hydraulic motor on one side. You have a hydraulic pump on the other side. And so it allows us to do that without, again, the big key with these, no fluid exchange between the systems or no fluid intermix between your two systems. Okay. The next thing we need to look at is where fluid is stored, and this is what we call reservoirs. So we store our fluid in the reservoir. Each system on an aircraft is going to have its own reservoir. And they are going to contain the fluid for use in that system. They're also going to compensate for changes in volume in the system. What do I mean by changes in volume? What's going to change the volume of a hydraulic system? When everything's hooked together, how will that volume change if it's a closed system? What? Temperature. Temperature will change the volume of the fluid by changing the density, so it will do that a little bit. So temperature fluctuations. What about the actual physical volume of the system? Any ideas? A leak? Yeah, I mean, it'll have a certain amount of fluid to compensate for that, but that'll only last so long. Any other ideas? So I'm going to pick up, we'll talk about actuators in a minute, but I'm going to pick up an actuator right here. There we go. Okay, so this piston slides in and out of this actuator. Okay. Notice that when it's retracted like this, there's a big rod in the middle of it. There'll be fluid around the outside here, but there's a big rod running down the center of the chamber, right? What happens when I extend this actuator? It opens up the entire volume of this rod that's in the middle. This is called an unbalanced actuator. So now our system volume has done what? Has it gotten larger or smaller? It's gotten larger. We've got more volume in here now inside of this tube, right? If I'm on this end, than if I'm at the far end. Okay, so our reservoir has to be able to compensate for the fact that the entire system, once everything's hooked together, that one does have schedule on it, or some kind of fluid on it. Once the system is all put together, all the lines are hooked together, everything else, it's not always going to stay the same volume. So the reservoir is where that actually goes. On one of the planes I worked on, when we filled the hydraulic system, you had to have the plane in a very specific configuration. Landing gear had to be down. Flight controls in neutral. You think what else? Flaps up, which is kind of neutral. Flaps where it had to be up. You know, things like that. And then you would fill the reservoir to say 60% full. Because when things actuate, it would do something, fluid would change. If our planes were up on jacks and somebody retracted the gear, the reservoir would drop to about, actually it was 80% full, would drop to 80% full. If we put them up on jacks, the gear would drop to or the reservoir would drop to 50% full. Right? Okay. People would occasionally go around service, they'd say, oh, the reservoir's at 50%, and they'd service it back up to 80. What's the difference between 50 and 80? 30. What's the difference between 80 and 100? 10% of the fluid would dump on the ground when we dropped the gear down. Because the reservoir would become overfilled when the gear lowered. It was the system that we needed extra volume when the gear was lower than when it was higher, right? So you drop the gear to go set the plane on jacks, and all of a sudden fluid would start dumping out of one of the reservoirs. Because the reservoir has an overflow, so you don't burst the reservoir. You don't want the reservoir to burst, right? At least we only lost 10% of the fluid and not the full, I think those reservoirs were about 5 gallons or so, give or take. So they does that valve. The other thing it's going to do is, remember I talked about with the hydraulic pumps, the one example I showed, these pumps are not self-priming. Piston pumps don't produce a lot of suction. So the one pump I showed had an integral impeller in it, a centrifugal pump to help that process, but most don't. Like if you look at the pump I passed around, you look at this pump, there is no impeller in these. They are purely a piston pump. So we have to get the fluid to the pump to make sure that it doesn't do what's called cavitate, or basically start sucking air or vacuum inside of the pump. And the way we do that is by forcing the fluid to the pump under a relatively low pressure. 12 psi, 15 psi, right? Nowhere near the system pressure, 3,000, 4,000, 5,000 psi, but just enough to maintain that there is always fluid coming into this inlet when the pump is running, so that it doesn't start to create a vacuum or create air and do what's called cavitate. And that's so head pressure or bootstrap pressure is going to make sure that that's always flowing, instead of putting an impeller type pump or a centrifugal pump in there. The other thing we have is bootstrap pressure prevents the hydraulic fluid from foaming. Why is that a concern? How's that gonna, why, any ideas why foaming can happen and how does doing this pressure prevent that? So what happens to the pressure around an aircraft when we go up in altitude? It drops, right? What happens to your bottle of pop when we crack open the cap and the pressure above the liquid drops? What happens? It foams, right? Trapped gas. Now there isn't nearly as much, it's not like the carbon dioxide that's in pop, but there is a small amount of trapped gas in hydraulic fluid. And so if that pressure drops on the outside, surrounding the hydraulic fluid, it will begin to foam. Not to mention you're running it through a pump, which is, sloshing it around and mixing it. It's flowing through actuators. There's a lot of turbulence in there. That can mix any air into it. So it can actually cause it to foam. How well does foam work to provide hydraulic actuation? Is foam compressible? If you have foam, can you squeeze it? Yeah, right? It's mostly air. Is liquid compressible? No, so hydraulics work because liquids are not compressible, so we don't want foam in our system that becomes compressible. Okay, so we don't want our system to foam. So really the reservoir does, 4 different functions that are all very important to making sure that the system works properly. Now there's different ways we can maintain the pressure and different ways we can construct reservoirs. So here's our first one. Okay, there's an example of a reservoir. I think it looks like a minion. The one with the single eye that wears a little glass there. Do anyone know the names? I don't know the minion's name. That's Bob? Bob the single eye? That's Kevin? Okay. You know what I should do is get a picture of him and just put it side next to it. Uh-oh. Are we looking it up back there? Okay, here's another style. I'm not sure what that looks like. Definitely not a minion. Okay. So there's 3 general styles. So the first one, which is actually the one I just showed you, is a bootstrap style reservoir. And it's a fluid bootstrap. So what we have here is, if we cut this thing open, and I'm going to go to a simplified picture. So if we cut this thing open, they're sitting relatively side by side now. You're going to have a, just show you where some lines are. The 72 psi right here. So this is putting 72 psi of fluid. Okay, this is the fluid in the reservoir, the green right here. And fluid is going to go out the suction line. That's the pump fluid supply. Okay, so that's going out to the pump. So that's under 70, so a little more than the 10 or 15 pounds I said earlier. In this case, it's 72, but it can depend. Different ones are different size. What you have is a big bobbin or spool type piston. So you've got a big diameter piston right here called the low pressure piston, and it's connected with a solid rod to a small piston over in this little piece going out to the right, this chamber. Okay? And what we do is when our pump is running, we take fluids coming out here, it goes to a pump. We take a small amount of that 3,000 psi fluid, we route it back to the reservoir, and we fill this little chamber right here that's going to push against the high pressure small piston. And that's going to try to drive this entire spool to the right. And now it's going to put 72 psi here. Anyone know how to figure out where that comes from? What's the ratio of these 2 pistons to each other? Any idea? 3,000 divided by 72. My phone's tied up at the minute. What's that? 41.6. So this piston, the big piston, is 41.6 times the area of the big piston is 41.6 times the area of the small piston. Okay? So that high pressure fluid is used to do that. Okay? You can see some of the other, there's a return line, right? A couple of return lines. That's the fluid coming back from the system. In this case, it's got a bleed relief valve. If this one's designed to be mounted sideways, that's to be able to burp air out of there, bleed air out of there. Okay, that's the bleed valve portion of it. What do you think the relief valve portion is? What's a relief valve do? Okay. This is where if this gets overfilled and this piston gets pushed all the way to this side and there's no more room for fluid, that pressure is going to go up to a point where it pops that relief valve open. And there would be typically a drain hose coming off of it to route it overboard so that you don't burst the reservoir. And then Skydrow gets everywhere. Either way, Skydrow gets everywhere. Down here, this area is just air. There's just a vent on this end, okay? And then they show a quantity indicator. This would have some kind of attachment to this piston. And so based on where the low pressure piston is, or sometimes it's down here at the bottom of the high pressure side, you know, depending on where that is, it does that. Now, what's the flaw with this kind of reservoir and how head pressure is related to things? What does it require for head pressure? It has to have an input pressure. So what happens when we shut our system off? There's no pressure. So some airplanes will have an accumulator, we'll get to that, to hold some pressure. Accumulator is a pressure storage device when the pumps are off. But when we would drain our accumulators, when you first turn the pumps on, they growled like you wouldn't believe until they got the air out of them, built that pressure up, and had that positive fluid flow. You could tell they were cavitating when you first turned them on if the accumulators were pressurized. So I do have one of these reservoirs. This is the one that always ends up dumping on the floor if I'm not careful. There's one right here. Okay. Now this one was designed to be mounted this way because it's got a breather up here at the top. Okay. You have your various ports at the bottom, piston inside, and in this case, as the pistons move up and down, this little red arm moves up and down. And see, it points to that. Let me think. I don't remember how this works. That moves. Something. There's another indicator piece that's missing, but then it allows you to see. So this is left system fill levels. So here is full with hydraulic pressure on, right when that bootstrap pressure is working. Here's full under 0 psi, full and refill. And it talks about fluid levels are for 70 degrees because remember pressure can make a difference there. And it tells you underfill at plus 20 degrees, underfill at plus 30 degrees. It talks about how to fill it, but this is linked to this level indicator to be able to send a level indication display to the cockpit, to the ICAS system. I want to say this was off of a 767. Can't remember for sure. But there's one of those. Is it leaking? Oh. We'll put it away before it makes too big of a mess. Okay. So that's our bootstrap reservoir. So it's fluid pressurized. Next one we have is our minion. And I don't have one of these to show you, but has anyone seen that one right there? In the 727, right? So 727 use pneumatically air pressure. So in this case, you have a reservoir, a tank basically. There is no piston or anything here. All it does is the airspace above it. You take high pressure bleed air off the engines or APU, and you use it to pressurize this space. This is kind of like the pop bottle, right? As long as pressure's on there, your pop bottle, even though there's no like piston pushing down on the pop, as long as the pressure is maintained, it doesn't foam, right? And if you were to punch a little hole in the bottom, it'd come squirting out, right? Here's our little hole at the bottom to the pump inlet, okay? There's some baffles in there so the fluid doesn't slosh around too much. But your suction lines that go out to the pumps and that kind of thing, and then your return up here. Here's your air bleed, and pressure relief valve. Again, if it overfills, it'll pop that open to dump excess fluid again so the reservoir itself doesn't burst. Okay. But essentially it's a tank. These ones have, the ones in the 727 do have a like a level indication on them. It essentially is like a float type level indication. You know, it floats at the surface of the fluid in there. And then the third type is a spring pressure. So here it looks pretty similar. It looks like a another kind of just tank. Now we have a piston that's in there that can move up and down, and there's a spring holding it. And I have one of these here. Now this has this little end on it. This is not for a bootstrap. This is not for a fluid pressure. This is just a quantity indicator on the end of it. Even though it kind of looks like the one down below, the one in my hand here, this is just for quantity indication. But you can see here the fluid would be down in this lower part. Here's our piston with seals, and we've got a big spring pushing down on the top of the piston. So as we fill it with fluid, it's going to push this piston up. You know, as the fluid, if the system volume increases, it'll be able to push the piston down. The spring will push the piston down, but it'll again maintain that head pressure on the fluid so that, again, it doesn't foam, to maintain positive pressure, you know, all those good things. So this one is dry. That one you can pass around, take a quick look at it. That one's being cut away. Nice to be able to see everything. So, okay. So those are the three most common types of reservoirs. Probably the most common you'll see nowadays are the fluid pressurized, the big one at the bottom, the first one we talked about. The spring pressure ones tend to be a little bit smaller aircraft, like corporate type stuff. There are still some air pressurized ones as well, but again, they tend to be a little bit older technology. So here's what one of those looks like on the outside. Now this one has an integral filter module on the end of it, where not only do you have the reservoir, but it's got a couple filter ports. So here's your pump suction, return, various returns, and servicing ports. You know, these often have a servicing port, like the 727. The remote servicing is down the hydraulic bay, and we can service all the reservoirs from one spot on the outside left of the airplane instead of having to go to each reservoir and fill it up. You can fill it from a single location. So with that, I'm going to go ahead and stop here, and we will take a break.